Okay, we can start. Today we continue a series of lectures on quantum dots, and the entire lecture will be dedicated to spin states in quantum dots. This is a subject which is very interesting from the fundamental point of view, because using spin you can probe interactions in quantum dots. It is also very important in the context of quantum information processing, because spin in a quantum dot is one of the first proposals to build qubits, quantum bits, so based on spin 1/2 particles. So we will get into quantum computing aspects of spin in the next couple lectures, but today we study the basics of quantum states of spins, and in particular the simple effects in single and double dots, which just have to do with bare spin, or can be understood only if you know that there is Zeeman effect, and the spin up and spin down acquire different energies in finite magnetic field. You can understand all these effects. But we will also try to get to more fancy effects like Kondo, spin orbit, hyperfine interactions. And you see the Swiss knife pulled out the blades. Those are all the extras, extra physics, extra functionalities in your devices that you can get if you study spins in real materials. So in semiconductors, in other materials, there are interactions of spin with lattice and interactions of electrons with themselves that lead to interesting effects. So that makes spin physics more exciting to study. You know, a lot of the material that I will cover, especially the basics of spin states, but also interactions as well, can be found in this review by Ronald Hansen and others, called Spins in Few Electron Quantum Dots. So this literally follows the title of the lecture. So I use heavily this review. I read it myself often, and I recommend it to you. You can get it on archive, and I actually recommend taking it from archive, because the published version on Reviews of Modern Physics has, for whatever reason, low quality figures if you download it from the APS website. So just go to archive and get the review. Yeah, first we pick up where we left last time. We'll review once again basic spin states of a single electron in a quantum dot. So this quantum dot is made in gallium arsenide, aluminum gallium arsenide two-dimensional electron gas by gates. And as they sweep the gate to more and more negative, they can make the quantum dot completely empty, and that corresponds to this never-closing Coulomb diamond. Right? So that whenever the diamonds close, it means you add another electron to the dot, and in this case, the last diamond does not close. So this is the last transition. Yeah.
How do you know when to stop tuning the gate? You know it's not eventually going to close.
Yeah, it's a good point. So there could be several things happening. Actually, it could be that there are closures, but you don't see them, because as you kick out electrons from the dot, you also make the potential in the dot more negative. And so it is has a side effect of raising the tunnel barriers to the dot. So the current through the dot drops, and you just at some point stop seeing it. So it could be that this will not be the last electron, but it would be a 7th electron, and there are 6 more that are invisible. So you tune the gate potentials until you convince yourself that this is the last one. And this is the best you can do in transport. You can also use spin states to convince yourself that this is the last one. Because if this dot is empty, now by adding 1 electron to the dot, I am adding 1 extra spin. And then the excited states of that spin, they should behave as excited states of spin 1/2 particle. So for example, here, remember the lines that run parallel to the diamond edges, those are, in quantum dots, those are the excited states. They could be orbital excited states, they could be spin excited states. And when they end in this diamond, then they lead to this diamond, it means they are the excited states of this many electrons. So in this case, when they zoom in on this region, they see, again, these two lines, the ground state and the excited state. And the separation is about 1 millivolt. And those are actually orbital excited states. So this is actually taken at 0 magnetic field, so we don't know the spin yet. This is just the basic.
So does the absence of an excited state ending on that n equals 0 also tell me?
Yeah, that's also a good indication that there are no lines running this way, and you can use that as an argument. However, oftentimes there are also many lines going into the 0th diamond. And there is a big discussion, why is that? It could be that the density of states is not flat, it has some modulation, and so you're just seeing some states in the leads. That could be one reason. Or there could be phonons. So you can still jump through an empty dot from one side to the other, mediated by a phonon, or if there are two resonances in the leads and nothing in between, when those two come on resonance, you'll get higher current, and those could show up as lines here. Actually, it's very nice that you're asking all these questions. They're often asked, well, how do you know you've reached the last electron? Because it is very remarkable that you can start with a piece of semiconductor with an Avogadro number of electrons, and by engineering your device, the potentials and gates, squeeze out all the other electrons and be just left with one little electron on the island. It is very difficult, and it is highly valuable, because that electron would then become the quantum bit, for example. And if you can make one and control it, that's a big step. And if you can make a chain of them, you can build a quantum computer. So these questions came up many times. And it turns out here you have to kind of go by intuition a lot. Or if you see such a clear picture, then it is quite reasonable. But you can do much better with a charge sensor. And I think I have a slide on that a little bit later. I will show you that we can know for sure when we reach the last electron with a charge sensor. OK, so once again, these extra lines that show up, they are simply when you increase the source-drain bias. You raise the difference between the chemical potentials on the source and the drain, and the two levels fit in between the source and the drain, the ground state and the excited state. And in that case, the current experiences a jump up, because now the probability to go is higher. You have two levels to go through. And in differential conductance, so the derivative of current with respect to bias, you get a line. So step means a line in derivative. So this is how you do spectroscopy on quantum dots, once again. And if you apply magnetic field, I showed this to you in an indium arsenide nanowire device last time, and now I'm showing it to you in a gallium arsenide device. Both the ground state and the excited states split by the Zeeman energy. So the Zeeman energy is just the energy between spin down and spin up. Spin down is lower in energy. That's because the effective G factor in gallium arsenide is negative. It is supposed to be negative 0.44. So if the G factor were positive, spin down would be the lowest energy state. So we just assign the lower line to spin up and the higher line to spin down. We cannot actually measure spin yet. We can measure it later. We cannot measure it yet. We could just label these lines: spin down ground state, spin up ground state, spin down excited state, spin up excited state. And excited and ground here refer to the orbital ground and excited states. And then there are spin splitting. And you can see that as you crank up the magnetic field, this distance between the two lines grows. That's just simply the Zeeman effect. So they've done it for a bunch of fields, and they've made this plot, Zeeman splitting as a function of magnetic field, in order to extract this G parameter, the G factor. And what they found is that they were actually expecting the dashed line, the 0.44, that's the gallium arsenide number. We will get to that in a moment, why it is not 2, for example, like for a free electron. But they found that the G factor follows another line. So this is a, here I just make a comment for now that G factors in quantum dots can be different than the G factors in the bulk. For some reason. We'll explain it later in the lecture. Or maybe some of you have a guess. Yeah. So once we get to that, so I will say more words about that. Okay. So we were talking about the most basic spin effect, the Zeeman effect, splitting of two spin levels for a single electron. Now let's add another electron to the quantum dot. Then we go into this manifold of states. The ground state, if we have two electrons in a dot, the ground state will be a singlet. Those electrons will be anti-parallel like that. So the ground orbital state, the lowest orbital, will be occupied by two electrons in a singlet state. And if we can also arrange these spins in a triplet like that, right? But those two electrons will not be able to sit on the lowest orbital because of the Pauli principle. Yeah? So Pauli principle will say that two electrons with the same quantum numbers cannot happen. So two electrons with the same orbital and the same spin is not allowed. So the second spin will have to go to the higher state. So then the lowest excited state at zero magnetic field for two electrons would be a triplet spin state, and the orbital character would be that the first electron will be in the lowest orbital and the second electron will be the next orbital. Is that clear? Yeah, so just Pauli principle means that if you're in a triplet, you occupy like that. The lowest orbital, one electron, second orbital. So the excited states are triplets. And you can have three different kinds of triplet. You can have both spins pointing up. That's called T+. You have both spins pointing down. That's T-. And you can have T0, which is a state like that. This plus this. That's different from spin singlet, which is this minus this. Yeah? So those are the states that you can have. Now you can do, you can see all these states in Coulomb diamonds. We will have to play the same game as we played in the last lecture and figure out, in this case for finite field, what would be the different energies of transitions between states of one electron and the states of two electrons. And some of them, you can see they have the same color. That means they are the same length. That's because it assumes that the Zeeman splitting here is the same as the Zeeman splitting here. So some of them are equal, so there will be some degeneracies. And so if you add them all up along the chemical potential axis, you will have these kind of chemical potentials. Yeah? So energies to add an extra particle to a different level. And as I told you last time, you can change the chemical potential with a gate. So all these chemical potentials will be aligned along the gate axis. But you don't see all of them because you have regions of Coulomb blockade here and here. And so they start showing up above Coulomb diamonds as a bunch of lines. And you can get these lines by extrapolating from green, red, blue, etc. to higher bias. So this is following the same logic as last time. I can spend more time on this if you guys have questions. This is somewhat tricky procedure. Mostly I want you to get a sense for what you're supposed to do. And if you encounter this in your research, you will be able to go back and figure out what all these lines mean. But if you have questions, I can answer. OK. So I want to spend a little bit of time with this diagram. So you have data and schematics of the levels. And the point is, for this particular data set, there is a very good match. And so they tune the quantum dots so nicely that you can see the textbook level correspondence in this data. And the different regions correspond to transitions from states with 1 electron to states with 2 electrons. For example, the main one here is the ground state transition. That's where the Coulomb diamond goes to 0 bias. So that's in the absence of spin. At this point, you have the same energy requirement to add 1 electron as you have to add 2 electrons, because you have tuned the chemical potential to such a position. If you add spin to this discussion, then the ground state of 1 electron will be spin up, and the ground state of 2 electrons will be a singlet. So in that case, this corresponds to a spin up to singlet transition. Spin down to singlet transition is here in energy, and the various triplet transitions are higher in energy. So each of the states at 0 bias gets broadened by finite bias like that, because you increase the window in which you can see these states. So that gives you these lines. So in particular, in this region A, for example, you are only seeing one state in between the source and the drain. And that state is the ground state transition, spin down, or spin up to singlet. Is that clear? So only one level here. And as you cross these lines, you start seeing more and more levels. So you start seeing 2, 3, etc. levels.
Why don't we see the spin up and spin down transition?
We do. This would be this guy, but you have to be inside this diamond. So.
But it's you're showing a singlet to. These are only between n. When the activation is 1 to 2, do we not see like transitions where you don't change the charge state?
Okay. I see what you mean. Along this axis, here you line up the transitions where you add another electron to the dot. If you want to stay within one charge, you are inside this diamond, and then the excited state, this one, is the one you're looking for. So, but it, it's the same levels, spin up and spin down levels. They're same and split. But you can put 1 electron in this level, or you can put 2 electrons in these 2 levels. Yeah? So the same quantum levels, but different charge. And so the difference is whether you pay a charging energy or not. So if you want to stay inside this diamond and just go a little bit up in bias, you haven't paid the charging energy. So you're just seeing the two levels, spin down and spin up, inside your bias window. That's all that happens. And if you go along this axis, then I label it spin up to singlet or spin down to singlet, because you actually have to add another charge to go from this diamond to this diamond. So here you don't see for example, this transition is dashed because you don't have enough charging energy to observe that transition. So you are inside Coulomb blockade. So you have to keep, when you're thinking about this, you have to keep in your mind the track of how many electrons are inside the dot at any given time, and which level is within the bias window. Those are two questions you have to answer. Okay, so I thought we would play a little bit with these transitions. And here I show you, well, it's fairly obvious, actually, that you can also do spin filtering using a quantum dot. So we were just discussing this pair of levels, spin up and spin down, for a single electron. So in this dot, by charging energy, we are allowed to have only one electron. So we are inside this diamond, n equals 1. But if we crank up the bias, like that, for example, then these two levels, they are within the bias window. So electrons will tunnel from here, and if it's a spin-up electron, it will go through the lower level and out. And if it's a spin-down electron, it will go through the higher level and out. So both spins are allowed to go at one at a time. Two electrons at the same time cannot stay too long. There will be too much charging energy. So they will, depending on these barriers, they might spend a little bit of time together, but they will try to escape very fast. But now let's tune the gate a little bit such that only one of these levels is inside this bias window. And that corresponds to being in this region A here. So in that case, the spin-down electrons are not allowed to go. Only spin-up electrons are allowed to go. So we made a spin filter which only allows spin-up electrons to go through. Well, we can actually make the opposite filter as well. We can make only spin-down electrons go. And that's when we come back to this region A. Remember, A was the region where we were only allowed to go from spin up to a singlet. So imagine that we already have a spin up in a dot, and the electron that jumps on the island can only form a singlet with that spin up. Well, that means that electron has to be spin down. So that means that if we just in the region A, we have this one level in a dot. We are between n equal 1 and n equal 2. So we have this one level, which is a level like that. There is already a spin down electron down there, and this level allows you to form a singlet state. So spin-down electrons will jump here, and they will come out. But spin-up electrons will not be allowed to go. They would have to go to a higher level. There is no energy for that. Now, this is actually the same device. We just changed the gate. We used to be an n equal 1 on this side a bit. And then we were allowed to pass only spin-up electrons. Now we tune over here. Now we are allowed to pass only spin-down electrons. We can select with a gate which polarity to go. So this is a neat little application for a quantum dot with just 2 electrons. You can make a spin filter. Remember, I already showed you one example of a spin filter with these quantum point contacts, right? So these were the quantized steps, and at zero magnetic field, they are 2e² steps. Right? And that's due to spin degeneracy. And then for the red trace, we lift spin degeneracy, and we have a step at 1e²h, means that spin degeneracy of subbands is lifted. And so if we tune the gate here at the lowest step, we are only allowing to pass one spin, the spin up, the lowest energy spin. With this technique, we cannot pass the opposite spin, though. We cannot pass spin down. But we can pass a lot more current because the conductance is very high. So, spin filters. Okay, to finish single dots, I will spend a couple of slides on Kondo effect because it is a very interesting phenomenon that involves interactions of many electrons. Kondo effect has a long history. It was first discovered in dirty metals. Their discovery was that the resistance of metals, when you lower the temperature, it normally goes down, but then at the lowest temperatures in dirty alloys, it started going up. And people didn't know for many years what was the answer. But now we know, and the physics is contained here. And for the quantum dot, it is like an example of a single impurity in a metal. Impurity in a sense that we have one electron there with a spin. And that impurity is fully controlled. So we can have enormous advantage at studying this Kondo effect with all this control. So Kondo effect is depicted here. It is an effect where this spin in the dot is allowed to see electrons around it, maybe through tunnel barriers. There are overlaps of their wave functions. And you can think of it like that. The electrons form a gas outside the dot, and they see spin, and they're attracted to that spin by spin-spin interactions. Let's just say dipole-dipole interactions of two spins. But actually, it's exchange. And then electrons that fly around in the leads, they form a screening cloud around the spin to make the total spin 0. So as if these electrons with the opposite spin to the spin on the dot spend a little bit more time next to the spin. And so they form this dynamic cloud, and on average some of them are trapped close to the spin a little bit longer. So they sit in this cloud, and they sit there for a few seconds, and they fly away. And for that reason, actually, in metals, resistance started going up because these impurities, these spins, they were localizing mobile electrons around themselves. They were not letting them go. Or where are you going? And it was happening at low temperature because this interaction, this Kondo interaction, it turns on below a certain temperature called the Kondo temperature. It is not a phase transition. It is kind of a crossover effect. So there is no thermodynamics that you can write in terms of phase transitions. Now, the proper language to describe Kondo effect in quantum dots is through co-tunneling processes, so virtual transitions, remember? The diagram is shown here. Imagine that you are at zero bias, so source and drain are equal, and you are in the middle of a Coulomb diamond, so there is no level in between source and drain, no level. But if you count up all the spins that are inside this dot, they give you a total spin. So the higher level has maybe a single electron, and all the lower levels are pairwise filled. That would be the simplest example. So there is one extra spin. And then if you open up these barriers a bit, it doesn't happen when they're too closed. But if you open them up a bit, you allow this co-tunneling process where spin down electron jumps on, and at the same time spin up electrons jump out. So you're not allowed to go, but you did transport an electron through this quantum dot. But you also flip the spin. Now, this happens to be the lowest energy process that you can have. Now, note, this only works on resonance when these two levels are aligned. This is a virtual process. It is difficult for it to occur because it needs to, you need to go to higher orders. And so when you break the symmetry between source and drain, the electron that jumps in and the electron that jumps out would have a different energy. And this process, the probability of this process goes way down. So then, keeping those two simple things in mind, that you need a spin and you need zero bias, this is your expectation for how you would see Kondo effect in a quantum dot. Remember Coulomb diamonds and maybe some excited states here, but then odd diamonds, the ones with spin, there you would have extra current around zero bias. That would be Kondo effect. And an even diamond with no spin, no Kondo resonance. So this is, I just looked around on the internet today, and there are many papers on Kondo effect. I found this one. This is work from Israel, where they made two contacts to indium arsenide nanowire. They have a gate underneath. So they make a quantum dot in between these contacts. And they sweep the gate. They don't know how many electrons they have. But they see these diamonds, these diamond shapes. And every other diamond, roughly, here it's a little bit hard to say, but pretty much every other diamond has this little black stripe, zero bias peak around zero. So a little higher conductance at zero energy, at zero bias. So that is a typical Kondo effect. Very interesting topic. If you apply magnetic field, this peak splits in two. Okay, that was what I wanted to say for spin states in single dots, more or less. We will come back to that a little bit when we talk about spin-orbit interaction. But there is a lot of interesting phenomena happening in double quantum dots. Also have to do with singlet and triplet states. So as a reminder, I plot again the double quantum dot charging diagram. Remember, in a double quantum dot, you have 2 degrees of freedom, the left dot and the right dot. You can tune them with the left gate and the right gate, with the left gate and the right gate. And you have a 2-dimensional map of charge stability, where you have indices like 0, 0, 1, 1. That means 1 electron on the left, 1 electron on the right. 1, 2 means 1 electron on the left, 2 electrons on the right, etc., etc. So you have 2 dots, and you can change the number of charges in both dots. And you have to go through such shapes, such honeycomb shapes in gate space. If you cross one of these lines, you add or subtract electron. This way you subtract from the right dot, and this way you subtract from the left dot. Sorry, the other way around. This way you subtract from the right dot, you change the right gate, and this way you subtract from the left dot. Left and right, I have to remember. I also use this kind of data to introduce, once again, the charge sensing technique for acquiring signals. So these lines are charge transitions. These are charge degeneracy lines where it costs you the same energy to have 2-1 configuration as 1-1 configuration, for example. So these are analogous to Coulomb diamonds, diamond lines or Coulomb peaks, but they are not obtained by measuring current. They are obtained by measuring directly the charge. So these little black pixels is when a charge detector senses that a single electron has left or come on the dot. The way this works is next to a quantum dot, in this case a double quantum dot, they put 2 quantum point contacts. These could also be quantum dots, doesn't matter. And then they send the current over here, not over here, not through the dot, but through the sensor. And an extra electron on this dot shifts a little bit the configuration of the sensor and gives a little kink in a sensor conductance. So the current through the quantum point contact is some kind of a curve with steep parts, steep slopes. Those are transitions between plateaus. So this is a pinched off quantum point contact, and this is the first plateau. And in between you have this steep part. And if you add an extra electron to the dot, this entire trace, it shifts a bit in gate space. So in this gate axis, this trace would occur at a different position. So if we sit at the finite gate, we would see a change in conductance. And that change in conductance is plotted in black. So they are changing a gate on the dot, so on the dot, and they see little kinks in the quantum point contact current. If they measure at the same time the quantum dot, they measure current at the same time, they see these Coulomb peaks. And okay, this Coulomb peak I can see very well, so I know that an extra electron jumped on the dot. And I can also see the kink here. Here, okay, there is a little peak. That's big enough for me to see. Actually, that's okay. And there is a kink. But here, there's nothing. So if I just measure current through the dot, it's so small, I cannot measure it. So I cannot see the Coulomb peak. But I can still see the kink. So with the charge sensing technique, that's what I said earlier, you can always find the last electron when it left the dot. And when there are no more kinks for a while, well, if it's you have your alpha factor, which is a conversion between a gate and bias, and so by changing the gate, you know how much energy you're adding to the dot. And so if you are at 5 times the charging energy and there are no kinks, the dot is empty. So that's pretty clear. In fact, in the group of Liev and van der Sijpen in Delft, using such devices with a charge sensor, they've developed an automated algorithm to tune to the few electron regime. They just press the button on their computer and it finds the last electron by itself. Because you just need to count the kinks. Okay, so once again, we are going to be looking at double quantum dots that have these honeycombs. We are going to look in particular at a double quantum dot that has 2 electrons in it. So double quantum dot with 2 electrons. Now there are 2 possibilities. 2 electrons can be each on one dot, or 2 electrons can be on the same dot. Now, from the point of view of quantum states or spin states, those are very different. There are very important differences, especially if we include spin. So first of all, let's think about spin states of 2 electrons once again. They can be a singlet state, right? Spins up, like spin up and down like that. They can be triplet states. So 3 triplet states, 1 singlet state. But now we can have a singlet state with 2 electrons on the same dot. Or we can have a singlet state with 2 electrons on 2 opposite dots. Those are 2 different states. In principle, they can have 2 different energies, depending on how we tune the chemical potentials in the 2 dots. Because in the first case, when the 2 spins are on separate dots, they are occupying 2 different orbitals in the 2 dots. And those orbitals, we can tune them separately with gates. And when the 2 electrons are on the same dot, then they are tuned together with 1 gate. So there is a difference. So there are 2 different singlets, and they are sometimes called singlet 1,1 and singlet 0,2. So 2 electrons on opposite dots, 1 on the left, 1 on the right, both electrons on the right dot in this case, on the downstream dot. Now, same goes for triplets. You can have a triplet with 2 electrons on different dots, and you can have triplets with 2 electrons on same dots. The triplets, the story is the same. You can have 3 of them in the first case, 3 of them in the second case. But if you think about singlet O2 and triplet O2, there the story from a single dot applies, that there is an energy difference between this singlet and the triplet, because now one dot is empty, the other one has 2. It's like a single dot with 2 electrons. And in that case, if you form a singlet, they can both go on the same orbital. And if you form a triplet, the second electron has to go up to the next orbital. And hence, there is a singlet-triplet energy difference between singlet O2 and triplet O2. Now, I want to introduce a concept of detuning. I already mentioned it very briefly in the last lecture. For that, you have to remember these bias triangles. Remember, at the degeneracy points, if you apply finite bias to a double quantum dot, at the degeneracy point at 0 bias, it will be just 2 points through which the current flows. But as you apply the bias, they become these triangles. And the axis perpendicular to the triangle, that's called detuning axis. And now I will explain why it's called detuning. It detunes, specifically in this case, the 1,1 levels from 0,2 levels. So if you have a 2-dimensional gate space, left and right, and there is a triangle, it can point in different directions depending on the relative coupling of the 2 gates. You don't know that a priori, but every time when you plot a line that goes from the base to the tip, you will be, for example, keeping the 1,1 states fixed, and you'll be shifting the O2 states like that. That just has to do with whether you renormalize this coupling such that you shift this ladder of states and you keep this ladder constant. So these diagrams, they show they show kind of 2 dots, right? The left dot and the right dot. But actually, the labels are split in 1,1 and 0,2. So for most part, what's on the right will be just 0,2 states, and what's on the left will be 1,1 states. So this is just a schematic for how transport goes. You first go and fill in 2 electrons in the different dots, and then one of the electrons jumps over. And we'll be looking at that process. So now, this is a double quantum dot system, and that means that there is a wave function overlap of the particles in the 2 dots. And that means that there is coupling between these quantum states. And of course, the states that are coupled, they have to have the same spin character. So this is shown here. This is the amount of coupling. Now, when 2 levels come in resonance, if they are coupled, they will repel each other. So there's an anti-crossing instead of a crossing. And the singlet crossing happens at a lower energy than the triplet crossing, like that. This is in the most basic case if you just consider exchange interaction between 2 electrons. So this will be our starting point. There is a finer splitting between singlet and triplet here, which comes from this exchange process. So this slide explains detuning. Detuning is a particular cut in gate space where you detune singlet O2 level with respect to singlet 1,1 and triplet 1,1. So the O2 ladder moves and the 1,1 ladder stays. And you can have coupling between these states. Now we're going to consider this kind of a transport process where we go from one of the 1-1 states, singlet or triplet, into a singlet O2. So we will be biased around here, and this state will be far higher in bias, unreachable. So we'll be looking at a regime where this triplet O2 is too high, not accessible, actually the way it's drawn right now it is accessible, but oh no, it's not, sorry, because this one is lower. So the transport cycle is as follows. You have this spin up trapped here. This level is in the bias window, so an electron can come in here, and it can have a spin up or a spin down, doesn't matter. All these levels are forming a singlet 1-1, triplet 1-1, these kind of states with this guy. And now the question is, okay, this electron, whatever it is, it wants to go over. And you find that it can't always do that. Particular if the electron net filled into this state, the 1-1 state, has the same spin as the one that we already have here, then they form a triplet 1-1 state, and that's fine. But to go across and keep the spin, you have to go via triplet O2 state. So this spin cannot fill the singlet O2 state. So this electron will be stuck. Now if it had an opposite spin to this guy, it could just tunnel over, form a singlet O2 state, and then escape successfully to the lead. So we are in a funny situation where we apply this large bias, and in principle we should be allowed to send electrons through, but due to this arrangement of spin levels inside the double dot, we cannot. And remember, this is a DC current experiment, so we're just applying a bias and we're seeing what happens. So maybe the first guy that comes in is the opposite spin. Great, it escapes. Maybe the second one is the opposite spin, it escapes. But the third one will be spin up, and it's stuck forever. So if we measure current on our DC current meter, we will not see anything, because we cannot see the first couple electrons, and after a few nanoseconds, nothing will be happening anymore. So it will be stuck. So this is called spin blockade. This clear? Spin blockade is a beautiful effect. It's been measured multiple times in different systems. Here it is in one of these quantum dots that are etched out of a semiconductor. The two quantum dots are actually here and here. There are a couple different layers. And spin blockade is this suppression of current at forward bias. So for forward bias, meaning that source and drain are aligned like that, we have exactly the situation, the arrangement of levels that I described in the previous graph. Actually, if you flip the bias, you reverse the bias, you get into this situation. So this level is still spin up and it's still down. But now this singlet O2 level is the one that's above. And so we can always find a spin down electron here to go through. So all the spin up electrons will be trapped here. They will not be allowed to go. Like in a spin filter in a single dot. They will not be allowed to go. But there is plenty of the other electrons, and they will just go through. So there will be some current. Spin blockade only works in one direction. This is an example from gallium arsenide. Here they show us 4 different triangles. This is the one I just discussed, the spin blocked triangle. This is the opposite bias. Remember, triangles point in the direction of current flow. So here, current flows from 1, 1 to O2, 1, 1 to O2. And here, current flows from O2 to 1, 1 in the opposite direction. And the triangles are pointing in the opposite direction. And there is plenty of current. And here, not much current. And this is for comparison for when you have just one electron inside the dot. Inside the double dot. And so with one electron, it's like this diagram. There is no difference between bias and there is no spin blockade, because whatever the electron is, up or down, there is always another guy with the opposite spin that can go. There is no blockade. So you need to have two electrons in a double dot to see this blockade. So remember, once again, in a single dot, we can have some spin filtering maybe, but there is always current. But in a double dot, we can actually shut down the current. This effect is extremely useful for qubits, because you can just bias the dot and let the electrons flow, and then the current will stop, and you know that you formed a spin triplet state. So you can use it to initialize a qubit in a triplet state. This is a finer point, but it is often observed these edges remain bright. So the current is completely gone inside the triangle. This is spin blockade, but the edges are still there. Can you tell me from looking at the diagrams why is that? Shawan. We have to look at this color. Anybody? It's this diagram. So what's special when we are on this edge? What is special about the arrangement of levels?
Oh, the electron can, the long electron can go in, but it can still can go out.
Right.
The long spin one.
So because these two levels are aligned, it comes in with a wrong spin, forms a triplet, but then it says, oh, if nothing's happening, I go back. And then after a while, the opposite electron comes in, and then current is allowed. So the edges, this is called spin exchange with the leads. The electron can spend some time in a dot, go back to the lead, flip the spin, come back with the right spin, and go through. So blockade inside and spin exchange with the leads on the edges. You can use spin blockade to figure out where you have singlet and triplet states inside the diagram. So this is an indium arsenide double dot, and you have a bunch of triangles, a finite bias, but this is a charge stability scheme. So every time you cross in your mind one of the dashed lines, you are adding an electron. In this case, you're adding electrons to the left dot, and in this case, you're adding electrons to the right dot. And it turns out that we saw spin blockade as expected at this 1, 1 to 0, 2 transition. So the one I was always talking about, 2 electrons in the opposite dots, or 2 electrons on the same dot, and we go from that to that. But then 2 triangles over, so this will be, let's count together. On this side it will be 0, 0, 0, 1, 0, 2, 0, 3, 0, 4, and on this side it will be 3, 1. So 3, 1 to 0, 4 also has spin blockade. You can see the little edges a little bit brighter. Couple over, so this will be, let's see, this will be 3, 1, then 3, 2, 3, 3 to 4, 2 also has spin blockade. There is a lot of extra current. There are different reasons for that, but and so on and so forth. So every time you have 2 odd numbers going to 2 even numbers, it turns out in this case you form spin blockade regions, and so the picture of states is the same. You have singlets and triplets. You have extra electrons in the dots, like 3, 3 and 4, 2. So you have 2 electrons extra in each dot compared to what we were talking about. Here we had 1, 1, and here we have 3, 3. But those extra electrons, they just form singlets, and they're at lower energies. They don't matter. So you can just think about the higher electrons. It tells you very nicely that electrons in this particular device fill spin pair-wise. So the first electron that goes into the dot is maybe like that. The next one is like that. The third is like that. The fourth is like that. So there's a spin filling as you cross these lines. And there is an extra way in which you can see that there is spin filling. That is also marked in this graph. Who can tell me? You have to go back to your quantum dot lecture. Yeah, they're alternating sizes. It's especially clear here. The first one is small, then the distance between these triangles is large, and then it's small again. And that can be interpreted as that when you add a third electron, you have to pay more energy, more addition energy, to go from 2 electrons to 3 electrons. So that means the third electron goes to the next orbital, but not the second electron. So the first electron and the second electron are on the same orbital, the third and the fourth on the same orbital. And so the first few of these transitions follow this nice pattern. So first you have a nice filling of spins, and then it gets scrambled for whatever reason. So these levels I talked about, again, this is the detuning. So the detuning axis will be like that, or perpendicular to this. This is 1, 1, 0, 2 transition. Perpendicular to this axis will be the detuning. By the way, these bright tips, that's where the triplet comes in. So triplet O2. So that's a very large bias, far away. This is a singlet O2, and a triplet O2 is here. If you keep increasing bias, you'll see both of them. But at low bias, these are the levels we're dealing with. If we apply magnetic field, they change. The way they change is, again, very simple, with Zeeman rules. Now, of course, singlets don't change. They remain the same. So the green line here is a singlet 1, 1, and the blue line is a singlet O2. And you have an anti-crossing between them. That's the exchange coupling of the two dots, tunnel coupling. Now the 3 red lines, that's what splits. And again, triplet 0 actually has no spin, so it doesn't split. And triplet 1, 1 plus and triplet 1, 1 minus, they split, and this is the Zeeman energy. So this diagram transforms like that. And in recent experiments, these people, this is again from Delft, they were able to see all these levels. And they have done something that also people do in atomic physics. They have done photon spectroscopy. So they shine some light on this dot, and they see different transitions. This is their data. This is again the detuning axis. This is 0. This is in microvolts. So this is again the same axis, except now this is, I got myself a graph from indium arsenide and a graph from gallium arsenide, but it doesn't matter. The same concepts. And once they apply a radiation to this sample, but these photons are not the photons you think about. They are called microwave photons. Their frequencies are gigahertz. So just to give you a scale, a wave of 1 gigahertz frequency would be 30 centimeters long, like more than about a foot. About a foot long wave. So 10 gigahertz would be 3 centimeters. This photon is this big. About an inch. I apologize. Inch. It's about an inch long wave. And in laser labs, in optics, we deal with hundreds of nanometer wavelengths, and maybe a micron. So these photons are really big, but they behave in many ways like photons. They are quantum particles. They are used in quantum information a lot, and this is what these people were doing. They were doing quantum information experiments, but at one point they just left these phonons on and swept some gates, and they saw these lines. So they were able to map out all these lines like that to transitions between these different levels in a double quantum dot. So you can see there is some shift that that comes from it's an artifact of their measurement, but you can see that as they change magnetic field, these two guys split, and that's expected because one of them is a singlet to triplet minus, and the other one is singlet to triplet 0. So the distance between them grows as grows this red arrow if we imagine increasing magnetic field. And so on and so forth. So they can map out this anti-crossing here between singlet 02 and singlet 11 by sweeping these arrows through. So they go into this regime and they see the two lines bending. So I think this was a beautiful experiment. And the reason why they see these lines, that effect is called the photon-assisted tunneling. So they set up their quantum dot. They measure, well, in this case, it's a charge sensing measurement, but you can do it with current. You measure current. And once maybe you are in spin blockade, so you're not allowed to actually go through, but you can go if you get a photon. So a photon can give you enough energy to go, and provide you with these extra lines where you see a signal in the current. So these levels in quantum dots can be mapped out using, for example, photon-assisted tunneling, but also a couple of other techniques as well. Okay. Now I want to show you something strange. This one is familiar to you from a couple of slides ago. This is a spin blockade regime. You can recognize it by these bright edges. This is spin exchange with the leads. And inside the triangles, current is very low. So it corresponds to this arrangement of levels. The two spins of the same orientation get stuck. That's spin blockade. And the current is not allowed. It's blocked. Now, we change something. We turn on magnetic field. Oh, all this current is back. Spin blockade is gone. Yeah, so it's allowed to go. What's going on? We are still in the same configuration. We added some Zeeman splittings, but not large enough to bring this one down. I can tell you that that's not the case. Something else is going on. So why would the current turn on? I don't want you to tell me the full microscopic mechanism, but just guess what could happen with these electrons that all of a sudden the current turns on. These levels, okay, they moved a little bit, but you can still, in principle, should be able to get stuck. All right. The answer I'm looking for is what is a necessary ingredient for spin blockade is that tunneling from 1,1 to 0,2 must conserve spin. So if that's the case, current will be blocked because there is no way for this guy to tunnel. But if this guy is allowed to flip the spin, like here, effectively, in this situation, this guy was allowed to go in, come back with a different spin, and so there was current. So for whatever other reason, also inside the triangle, if the spin conservation does not hold. You can be in a situation where the current is lifted. So in this particular case, spin-orbit interaction lifts spin blockade. But there are many other ways. Here are the main two ways that I want to talk about in this course, and some of it today. It's a couple of different interactions that spin can have with the lattice, with its surrounding, that would lead to lifting of spin blockade and to many other interesting effects. And some of them are bad and some of them are good, depending on what your application is. But let's go through these. The first one is spin-orbit interaction. Spin-orbit interaction is the same effect as you maybe remember from atomic physics, where electric fields from the core, from the nucleus, or by Lorentz transformation, inducing a magnetic field on the electron. Here, electron is this big wave, and it's flying through the crystal lattice, and there are various electric fields embedded in the crystal. And this similar way as to relativistic effect, these electric fields create an effective magnetic field that acts on a moving electron. So this diagram. And since this is an interaction with the lattice, you can actually give and take energy from the lattice. So this is how you can, for example, create spin relaxation. You could be in this spin-up state, flying around, and interact with a phonon, which is a vibration of the lattice, and give away your energy and go into the spin-down state. And actually, in gallium arsenide, like I said, this would be the ground state, and this would be the excited state. So this is some fictitious material. Hyperfine interaction is an interaction between electron spin and nuclear spins. Nuclear spins. So in an atom, electron would interact with the nuclear spin of its nucleus. But in a crystal, electron is a wave packet that spans many, many nuclei. In principle, it can span 1 million nuclei in a typical gallium arsenide quantum dot. So you have to think about one spin living in a wave function overlapping 1 million nuclear spins. So this kind of picture. And all these spins are fluctuating and imposing different interactions on the central spin. So this interaction actually is not capable of taking energy from the electron spin. That's because the gyromagnetic ratio of nuclei is much lower than that for electron. The nuclear mass is about 1,000 times larger or more. And therefore, the Zeeman splitting of the nuclei is much smaller. So you can't actually flip the electron spin and give it to the nucleus if any magnetic field is involved. But at zero field, it is a powerful effect. So here are two spin blockade detuning cuts. Remember the detuning axis, detuning between 1, 1 and 0, 2. But actually the same thing happens along the whole axis. So we can just look at the magnetic field axis mostly in these two cases. So this is a spin blockade regime. And black means low current, no current. And red and blue means high current. So red is the highest, blue is a little bit lower. Two different regimes. We tune the dots differently. And in this case, we have current around zero field and no current at finite field. A spin blockade, this spin conservation is violated around zero magnetic field. And here, completely opposite. Actually, spin conservation is the strongest at zero field, and it's increased. The current is increased. Spin mixing is increased at higher field. So the faster spins mix together, the larger the current, because more spins can go through the spin blockade regime. Yeah. So the two regimes actually were hyperfine interaction dominates and spin-orbit interaction dominates. And the reasons are what I explained in the previous slide. Here, current is highest at zero field. And that's because, like I said, if you apply a little bit of field, electrons will have this much energy difference, but nuclei will have this much energy difference. And so you cannot do a spin flip and flip electron spin and give it to the nucleus because there is a huge energy mismatch for that. So that process becomes very inefficient. You can still have hyperfine interaction, but it is very weak. So in this regime, hyperfine interaction produces this kind of peak in current at zero field, and the spin blockade is lifted at zero field. The spin-orbit effect is the larger you make the energy difference, the better. The relaxation goes faster. This is a very naive way to explain this, but it's roughly correct. And so if you increase magnetic field, you increase the Zeeman splitting, and the spin-orbit interaction becomes more effective, and you get more current through this dot. Actually, strictly speaking, spin-orbit interaction cannot have any effect at zero field because the Hamiltonian is time reversal symmetric. I'll talk about this a little bit more in the coming lecture, I think. So we will finish today with discussing hyperfine interaction in a little bit more detail and leave spin-orbit interaction for later. The hyperfine interaction is this Hamiltonian. If we write the full spin Hamiltonian, it will have the Zeeman part like before. And we have to sum over all the nuclei. These are the nuclear spins II. And these are the hyperfine couplings between individual spins and the electron. These guys, A's, they depend on the kind of the raw coupling determined by the orbital symmetry in the material, so by the material specific symmetries, and by the amplitude of the electron wave at the position of each nucleus. So if you have a quantum dot in the kind of the lowest orbital state, maybe the electron has the highest probability in the center of the dot. And so the nuclei in the center of the dot will couple a little bit stronger than the ones on the outskirts of the dot. So that is all encoded in these AIs. But remember, these I's, they are random. Unless you do something special to them, they are not very sensitive to environment. The Zeeman splitting is very small, so it's very difficult to overcome temperature by applying magnetic field. So if they're let on living on themselves, they are completely randomly oriented. And so if we just ask ourselves what is the total field experienced by the electron from all these nuclei, we have to add them all up, and they will all be random. So on average, it will actually be 0. But at any given instance of time, it will be some small field of the order of this coupling constant divided by the number of nuclei. So it turns out in gallium arsenide, the strength of this A is pretty large, 5 Tesla. Very large field. So if we just had one nucleus, it will have a huge effect on the electron. The nucleus flips and electrons go, ooh. But we have 1 million. So we have to divide this by square root n, which will be several thousand. And so from that 5 Tesla, it comes down to about a millitesla fluctuating field. So the field will be anywhere between 5 Tesla and minus 5 Tesla. Most of the time it will be 0, and most often it will be within 1 millitesla of that 0. Okay, I think we'll stop here and carry on with spin-orbit interaction and spin qubits in the next lecture.